In this video, I will show you how to run analysis of variance in Jamovi. Let us start by loading our dataset. In this dataset, we have information for 47 children, including their sex, home language, condition in an intervention study, and some measures taken in kindergarten with the letter K, so a nonverbal ability, letter knowledge, receptive vocabulary, and word reading fluency, and measures taken in grade 1 and grade 2, including vocabulary and word reading fluency, and a final measure of word reading fluency post-intervention. Some of these data are real, some are simulated. For our first example, we want to see if sex or home language affects vocabulary in kindergarten. And when we say affects in statistical analysis, we do not imply causality. We're just asking if there is an association. So we want to see if receptive vocabulary measured in kindergarten differs between boys and girls or between children who have a majority home language versus minority home language, or an interaction between these factors. To run an ANOVA, we click on ANOVA, and then the kind that we're interested in. Here we have no repeated measures, it's just grouping factors. So we click on regular ANOVA. Our dependent variable will be vocabulary in kindergarten, and our fixed factors are sex and home language. And this is our ANOVA table. The sums of squares, degrees of freedom, mean squares, F ratios, and p-values. Before we go on to actually interpret this, we must go and check the assumptions for the ANOVA. And the assumptions include homogeneity of variance and normality. We see that the p-value for the homogeneity of variances test is high. So we do not reject the null hypothesis that the variances between the groups are equal. The normality test results in a low p-value, which means that our data aren't normally distributed. This is a reason to not proceed with analysis of variance and not interpret it. However, the ANOVA is relatively robust to modest deviations from normality. So unless our data look horrible, we might proceed with caution. This is not a horrible QQ plot. So we might proceed with interpreting this analysis while noting the problem with the normality and stating that the ANOVA is typically robust to modest deviations from normality. So let us add the measures of effect size to our table and go on to see what we have found. We see that the effect of sex is not statistically significant. The effect of home language is statistically significant, and there is no statistically significant interaction between these two. They suggest that whatever the effect of home language is, it is not different between the two sexes. Now, this video is about showing you how to run the ANOVA itself, and it's not really a lesson in analyzing these data, because as you know, if we were actually dealing with real data, we should have started with looking at the data, looking at the descriptives, and making sure everything is fine before we proceed to analyze anything. You'll see soon why I'm mentioning this. Here we have an effect of home language, which is significant. And although you may be able to imagine what it concerns, there's nothing here to tell you what the effect is. In order to understand anything about the effects that are statistically significant in an analysis of variance, you must look at the values. So in this case, to look at the values, we will create an interaction graph with both of our independent variables in this panel where we select the graphical display. Marginal means plots is what we're asking for. It was already checked. So all I had to do was to send these two variable names into the specification of the first graph. And I can look at the graph right here. So in this graph, we have sex on this axis and two different lines for majority and minority children. If I wanted the opposite, to have home language on the axis and two different lines for the boys and girls, I would have to change the order of these variables in the specification. So the first one goes on the x-axis, the second one goes in different lines. In whatever way this is presented, you see that the two lines are approximately parallel. This is consistent with the fact that there is no statistically significant interaction. We also see that the majority language is higher than the minority home language. Actually, the previous graph made this clearer. So we see that the line for the children who have the majority language as home language is completely above the line for children who have a minority language as their home language, which makes sense given that the receptive vocabulary was measured for the majority language. However, another thing you are seeing here is that these error bars are huge, indeed way larger than these error bars, especially for girls, but to some extent also for boys. And that's because there are very few children in this group. So this analysis is not really interpretable because of the very small sample size that doesn't allow any conclusions to be drawn regarding differences between individual cells. So this is only an example of the procedure. In this particular case, there is no statistically significant interaction, and the factor that does have a statistically significant effect only has two levels. So it is clear what is different from what. Children with a majority home language have a higher average receptive vocabulary than children with a minority home language at the age of kindergarten. That is our finding, and that is what we would report along with the results from the ANOVA table formatted as necessary for IPA format requirements. Let us now move on to another example, this time using a repeated measures approach. In our data, we have a simulated study of an intervention. So some children were in an intervention condition, some were in a control condition. The intervention was supposedly about reading, and so we expect to see some effects on word reading fluency. We actually want to see if the intervention improved the reading fluency of the intervention group. And the way to analyze this is in comparison with the control group. Because it is the same children who are measured before and after the intervention, this involves a repeated measure. Whenever a repeated measure is involved, we have to run a repeated measures ANOVA, even if there are other independent variables that are not repeated measures. So let us go back to the ANOVA menu and choose repeated measures ANOVA. This formulation requires a different arrangement of the data. Like for the t-test, the previous analysis of a factorial ANOVA requires each case to be on a row, and because all the factors were grouping factors, this means that the data for our previous analysis of variance were just on different lines. So sex and home language were analyzed as predictors of receptive vocabulary, just different columns. This time, going for the repeated measures, we have the same children receiving the same test twice, before and after the intervention. So although the condition variable is between children, so it's a variable in its own right, the other independent variable, which is time, which is before and after intervention, is not a variable. Actually, there are two columns. There is word reading fluency measured in grade 2 as a baseline, and word reading fluency measured after the intervention. This is what this variable is. So these two variables form the two levels of our actual independent variable for the analysis, which is time. So this is how this works. It is the same as it was for the paired samples t-test. Our repeated measures factor, I clicked on this that says repeated measures factor, and this lets me edit it. So I'm deleting that, and I'm typing time. I'm giving it this title. And then the first level of this variable is before intervention, and the second level is after intervention. So I'm making up the factor with the repeated measures in the definition of the analysis. The time factor is not a variable in my data. Rather, the levels of this factor are variables in my data. And as you notice, what I typed here appears down here. And this is where I actually pull my variables to. So Jamovi took this label. This is the first level of my factor before intervention. It was copied here. And so I have to pull the before intervention variable into this cell. So that was this one. And then the after intervention variable is this one. So now I have the two levels of my time independent variable entered as repeated measures. And as you see, Jamovi already begins to work on the ANOVA table without any other specification. This is comparing every child before and after the intervention. However, not every child received intervention. Only the children in one condition received intervention. The other children were a control condition. And that's how we're supposed to test interventions, because we want to account both for retesting as well as for growth and maturation that occurs independently of the intervention. So condition is a between subject factors, as it's called here. So this is actually a mixed design analysis of variance. And now we get two ANOVA tables because Jamovi presents these according to the strata, each with its own residual. The total sum of squares is the total of all of these. And we see that there seems to be an effect of time and an interaction between time and condition, and no effect of condition. What does this mean? We always need to check the graphs before we can understand what the results mean. However, before we get to the graphs, there's something else we need to do. Even before we say what we found, we need to come to the assumption checks. And we need to check the homogeneity of variance for our between participants variable, which is condition. And we see that for both of these, there is homogeneity of variance. Neither of these p-values is too low, although this one is close. It's not less than 0.05. So we can not reject the null hypothesis that the variances are equal, which is good. We can proceed. And if I click on sphericity tests, I get nothing because of this reason that is stated here. The repeated measure is just before and after intervention. So in terms of repeated measures, I only have one difference, the difference after minus before. There aren't two differences that must have equal variances. So the sphericity test does not produce any interpretable output because there's nothing to be compared. And so the correction factors here are equal to 1. There's nothing to correct. If this was a situation in which there was significant deviation from sphericity and there were correction factors here, what I should do would be to click, for example, on Hunefeld, and then instead of reading the none line, read the corrected line. Now the corrected line is the same, it has exactly the same values as the none line because there's nothing to correct for. If there was a need for correction, I would need to report these corrected rows instead from the ANOVA table. So now I don't have to do this, so I click back none, so no correction, and I can use these values. Let's see what the effect looks like. We want to see the effect of both independent variables together because we want to see what our results mean. There was a significant interaction. Indeed, here we see that the two lines are not parallel. This one seems approximately horizontal, and this one seems to be going up. This makes sense because this is the control condition, and there doesn't seem to be any change from before to after intervention because there wasn't much time between the two measurements. However, for the intervention condition, we see an increase in scores. This line goes up. So the interaction between the variable time and the variable condition or group is that the difference between groups is not the same at the two times. The difference between the groups is very little before intervention, but much bigger after intervention. Or you can say that the effect of time is not the same in the two groups. The effect of time in the control group is no effect. The effect of time in the intervention group looks like a positive effect, looks like an increase. So that's what the interaction means, but we don't know which of these points are different. Is this point significantly higher than this? So do we have higher fluency scores in the intervention group than in the control group after the intervention? Or do we have higher fluency scores in the intervention group after compared to before the intervention? This is not stated anywhere here. In order to figure it out, we need to run post hoc tests. And because we're interested in the interaction, so to compare individual combinations of conditions, we have to bring the interaction term into the post hoc tests and leave the selected two key correction here, which corrects for the multiple comparisons, and read this table. To read this table, we need to see that each line is a comparison between a pair of cells, a pair of combinations. So before intervention control compared with before intervention group. Before intervention control group compared with after intervention control group. Before intervention control group compared with after intervention group, and so on. So let's just go and check which of these differences are statistically significant. The only one that survives the correction and is statistically significant is this line. Not the last one, the second from last. Which comparison is that? This is the comparison of before intervention group versus after intervention group. That's the only statistically significant difference. So the statistically significant difference concerns the slope of this line. It says that the children in the intervention group obtain higher scores after the intervention compared to before. There is a statistically significant increase in scores for the intervention group. No other point pair is statistically different. All the other pairs are indistinguishable. And this difference is actually the cause of the statistically significant interaction that we see here. In addition, we see that there is a main effect of time, which means that on average, all children considered together, the fluency score after the intervention was higher than the fluency score before the intervention. However, it would be wrong to state that in the conclusion. It is actually not possible to interpret main effects in the presence of significant interactions. Because here we have a significant interaction, this means that the interpretation of the main effects is ambiguous, questionable, or even incorrect. If there is a significant interaction, we have to look at the graph and run the post hoc pairwise comparisons to see what actually was different and report that as the difference instead of the main effects. Finally, we can add the effect sizes to our ANOVA table, which we also will probably want to report either the partial eta square or the eta square. Do not get these two confused. And that's what you need to know to be able to run and read an ANOVA in Jamovi.